on.
All right. Well, are we bridged over? Yep. I can't see the other side, so
Yes.
we are bridged over. Okay, cool. Hello, everyone. Welcome to the 2020 AMC 10A live solve today. I have no idea what you guys are seeing, so hopefully this is working. But so we have two very wonderful teachers. My partner, her name is Alina. She's a JMO winner and attended MOP, the summer camp, 3 years coaching her local math team, and she really likes the letter M where it's not supposed to be. So,
And my partner today is Eric. He was also a JMO winner this year. He is a 5-time AME qualifier, and he swims.
yeah. So we're super excited to live solve these problems for you. Obviously, this is different from a normal live solve because we have taken these problems on the actual test before. I remember it was my year that year when I missed JMO qualification by half a point. So
No!
this brings back memories. But let's get started. Because of what we like to call copyright issues, unlike normal live solves, we can't have the problems up here for you. But Art of Problem Solving, if you want to follow along with our problems, you could go to artofsolving.com, and then you could go to the AOPS wiki, and they will have all of the problems listed for you. So you could go there, and you can check out those problems, even though we might not have them displayed. So I think we can get started then. So I think we can start with problem 1. Isn't everyone muted? Are we? Is there a technical issue going on?
There would be a slight problem if we were muted.
The ones talking are muted. Okay, well we're not muted. So there's like you can't hear us.
Very, very strange.
If they can't hear you, well,
It's okay. We can communicate with writing.
yes.
Oh, is it working? We are
Is it
audible?
working? Are we? No, I don't think we are. This is really weird.
Working. It's working. We're good. We're great. This is wonderful.
Okay. Why don't we all try that again? Because there would have been technical difficulties. So let's start from the very beginning. Welcome to our 2020 AMC 10A live solve, an entire, 4 days, 5 days, 4 days before the actual competition. So I am joined by a very wonderful teacher. Her name is Alina. She's a JMO winner and a MOP attendee last year, 2022, and this is her 3rd year coaching her local math team, and she really likes the letter M in places where it's not supposed to be.
And my co-TA today, we are joined by Eric, and he is also a JMO winner in the year 2022. He is a 5-time AME qualifier, and he is a swimmer as well.
Yeah, so we can't, because of what we like to call copyright issues, we can't really show these problems on the screen. That's what they told us. But if you want to follow along with the problems, you could go to artofproblemsolving.com to the AOPS wiki, or you can probably find the problems online. You can just follow along with that. Again, we're really sorry we can't show the problems on screen, though we will be referring to them, so we hope you understand what we're referring to. And also, as some of you guys have thankfully figured out and let us know that you could not hear us, if you go to your Zoom link and you send a direct message to Chat Relay, after about 10-ish or so seconds, it will show up underneath here, and then hopefully we will respond to your message. So that's a really nice interactive part of this. So why don't we get started? So Lena, do you want to take problem 1 for us?
Sure. So here is our first question. What value of x satisfies x minus 3/4 equals 5/12 minus 1/3. And for this, we just need to isolate the variable x over here, and we do this by adding 3/4 to both sides. So we get this nice expression on the right and just x on the left. And from here, we just need to bring it to a common denominator. You'll notice that we have a 12 in the denominator here, we have a 3 here and a 4 here, and 3 and 4 come together to make 12. So bringing it to a common denominator is actually not that difficult in this case. We just need to bring it to the denominator of 12. So we have x is equal to 5/12 minus 4/12. We get this by multiplying the 1 up top by 4 and the 3 on the bottom by 4, plus 9/12, and we got this by multiplying the top and bottom by 3. And from here, we can just do the math. So we get, math is difficult, 10/12, and this simplifies to 5/6. We get this by dividing the top and bottom by 2. So the answer to the first question is 5/6, which is answer choice E.
Yeah, very nice. So we can just keep going from here. So we have problem 2. Our numbers 3, 5, 7, A and B have an average of 15. So what is the average of A and B? Sorry, so we have 3, 5, 7, A and B. They add up to 15. So 3, 5, and 7, well, they already add up to 15. So I know A and B, they cannot add up to anything else. So A and B add up to 0.
Wait, hold on.
No, that's all right. They have an average of they have an average of 50, which is the sum is 75. I did not read the question right. That's why I have the question up there. They have an average of 15. That means 5 numbers. Their sum is 75. So A and B's sum is 60. Divide that by 2, and we get 30 for the average. Will there be a recording? Yes, there will be a recording of this. So if you don't want to have your real name in the recording, you can change it right now, just so you guys know. Anyway, let's keep going.
Next question. So this says, assuming A is not equal to 3, B is not equal to 4, C is not equal to 5, what value does this simplify to? And so you may notice some common terms here. Specifically, we have A minus 3 and then the negative of this here, and we have B minus 4 and the negative of that here, and C minus 5 and the negative of that here. So what we do from now is, well, first of all, we have properties of multiplication that allow us to rearrange terms. So we can simplify this, or at least make it easier to work with, by rearranging the common things so that they're one over the other. And after this, we can notice that we can factor out essentially an identity 1 over 1 from each of these fractions, leaving us with -1 from each term. So this simplifies down to -1, and this simplifies down to -1, and this one as well. And doing this multiplication, we get to an answer of -1, which is answer choice A.
Very cool. Okay, we have 2 hours for this, so I think we should just go a little faster on the other questions. Okay, question 4. A driver travels for 2 hours at 60 miles per hour. Should write this down. 2 miles at 60 miles per hour. And then her car gets 30 miles per gallon of gasoline. That's a pretty good, actually. She is paid 50 cents per mile, and her only expense is gasoline at $2 per gallon. I wish. $2 per gallon. Sorry. What is her net rate of pay in dollars per hour after 6 months? I'm sorry. This is like some wholesale price we've got going on. Should be 2 hours. So she goes 2 hours at 60 miles per hour. That's 120 miles. You just multiply those. At 30 miles per gallon, that's 4 gallons of gas. She used, so that's $8 she had to pay for gas, but she has paid 50 cents per mile, which means that she gets $60. That's not right. At $2 per gallon, 60 miles. 2 That's 30 miles per gallon. She's paid 50 cents per mile. So 60, right? Yeah, that looks right, which is 52, but she traveled for 2 hours. They want dollars per hour, because the answer choices weren't lining up. You want dollars per hour, which is 20, because she traveled for 2 hours. At 52 miles, that's 26 miles per $26 per hour, which would be our answer. There we go.
We're on our
$2 a
first round
gallon.
number question, which is question number 5 at a milestone. So here we have this lovely equation here, the absolute value, and it asks for the sum of all real x such that this is true. And the way we deal with absolute values is we can break it into 2 different questions, dealing with the positive value and the negative value. So if we start by looking at the positive value, we have x squared minus 12x plus 34 equals 2. And from this we get x squared minus 12x plus 32 is equal to 0. You can notice that this factors into having roots of 8 and 4. This is x minus 8 times x minus 4. You can validate this by seeing that 8 and 4 add up to 12, and 8 times 4 is 32. So this gives us 2 solutions, which are 8 and 4. Dealing with the negative case, we do essentially the same thing, but just switch the sign on the right-hand side. So here we have it's equal to negative 2, which gives us the expression x squared minus 12x plus 38. 36 is equal to 0. This is the square of x minus 6. So this gives us one solution, which is x is equal to 6. And the question asks us for the sum of all of these solutions. So this gives us 8 plus 4 plus 6, which is 18, or answer choice C.
Yeah, very good. I would like to point out that if you do try to blindly use Vieta's formulas on this, you will be tricked because there is a double root. So thankfully, there's no 24 in the answer choice, so like they weren't that mean to you. But anyway, question 6: How many? For I think someone asked in the chat how we could see the questions. If you go to Art of Problem Solving link, if I just copy that over and put it on the slide for you, you can go to those problems there. Oh, you can't see that. This is great. Yeah. Oh, please. Well, I fixed this. But yeah, so you could go to that link if any of you can see it. Why can't I change the color? Anyway, and then you can follow along. Again, we can't show the problems because MAA doesn't technically let us. So
Link.
Oh yeah, thank you.
Link is in
Thank you.
chat.
Thank you to whoever posted the link in the chat. I don't have to fix the color anymore. Anyway, question 6: How many 4-digit positive integers with no leading zeros having only even digits are divisible by 5? So I'm given a 4-digit number, and I know my last digit is divisible by 5, so it has to be 0 or 5. But we know that every digit is even, so it can't be 5. It has to be 0 up here. Then for my tens digit, it can be 0, 2, 4, 6, or 8. My hundreds digit, 0, 2, 4, 6, or 8. And then my thousands digit has to be 2, 4, 6, or 8. Remember, no leading zeros. So that's 4 ways times 5 ways times 5 ways times 1 way. They're all independent. So 4 times 5 gives me 100 possible numbers.
All right, so the next question asks us about magic squares. And it is really unfortunate that we can't show the wording for this because it's quite long. So we have 25 integers, and they are arranged in a 5 by 5 square. So we have 5 per row and 5 per column. And These integers go from -10 to +14 inclusive, and the sum in each row, in each column, and along the main diagonals are all the same. And we are asked for the value of the common sum. So one thing to notice here is that if we were to add up all of the numbers in the grid, we would get 5 times the sum of the numbers in a row. And we know that the sum of each row is the same. So if we just find the total sum of the numbers and divide by 5, we will have the row sum, and that is the common sum that we're looking for. So we just add up all the numbers from -10 to +14, which leaves us with the sum of the numbers from 11 to 14, which is 50. And this is 5 times our row sum, so we just divide by 5 to get our common sum, which is 10. This is answer choice C.
Yeah, I forgot AMC problems have answer choices. Let's go to problem 8. What is the value of 1 plus 2 plus 3 minus 4 plus 5 plus 6 plus 7 minus 8 and so on until minus 200? So it's something like this. Oh god. And so on until 200. So a couple ways we could do this. The fastest way that I see is we can sum everything from 1 plus 3 plus 4 all the way to 200, and then we can subtract 2 copies of 4 plus 8 plus 12 plus all the way up to 200. Remember, we have to get rid of 2 copies because the first copy knocks us down to 0, and then the second copy knocks us down to -1, which means we're subtracting all of this down here. And so these are just both pretty simple triangular sums. Hopefully you all know how to do this. So it's 200 times 201 minus 2 over 2 minus, so this is 8 times 1 plus 2 plus all the way until 50. So minus 8 times 50 times 51 over 2. Really hoping I don't make a computation error here. This turns out to be 20100 minus 200 times 51, which is 20100 minus 10200. Correct me if I'm wrong. Which goes out to be 9900. Answer choice B, like that.
All right, so the next question is another word problem. A single bench at a school event can hold either 7 adults or 11 children, and then they connect these bench sections end to end and seat an equal number of adults and children. It's asking for the least possible integer value of n, which is the number of bench sections you can join to seat an equal number of adults and children. So essentially what this question is asking us, well, first of all, it's to find the LCM of 7 and 11. And because they're both prime, the LCM is just 77. And this tells us that there has to be 77 adults and 77 children. And from here, we just divide by 7 and 11 respectively to get the number of benches in each case. For the adults, that gives us 11 benches, and for the children, that gives us 7. So our final answer is the sum, which is 18.
Very cool. Let's go on to problem 10 now. So we have 7 cubes. I drew 3.5 here. Volumes 1, 8, 27, 64, 125, 260. So they have side lengths of 1 to 7. Stacked vertically to form a tower in which the volumes of the cubes decrease from bottom to top. Biggest block on the bottom. Except for the bottom cube, the bottom face of each cube lies completely on top of the cube below it. What is the total surface area of the tower, including the bottom, in square units? So we just want total surface area here. Okay. We have, basically the key idea here is to realize that since my bottoms are completely stacked, like the bottom of this cube, for example, is completely on top of this one. So like my area here, for example, would be 7 squared minus 6 squared. The area here will be 6 squared minus 5 squared. The area up here will be 5 squared minus 4 squared, and so on. So let's just start by counting all of my faces that are vertical, basically. That are horizontal. And then because the sideways ones, those are easy to calculate the area of. Let's do the little like ring-shaped, L-shaped sort of things out here. So we have 1 squared on the very top, right? Because there's no cube on top of that. Plus 2 squared minus 1 squared, plus 3 squared minus 2 squared, plus 4 squared minus 3 squared, and so on, plus 7 squared minus 6 squared, plus 7 squared. So we take that, we can simplify this. So we know that this series sort of telescopes, like we have a positive 1 squared, then a negative 1 squared, positive 2 squared, negative 2 squared, positive 3 squared, negative 3 squared. So this comes out to be 7 squared plus 7 squared, which is equal to 98. And then we could do the sideways ones, right? So we have 4 of these sides, and then it's 1 squared plus 2 squared plus 3 squared, all the way to 7 squared. These are my vertical sides. Can't spell. Vertical sides. Sum of 1 squared to 7 squared is 7 times 8 times 15 over 6, which gives me 140. So 4 times that gets me 560. 560 plus 98 gets me 658, which turns out to be answer choice B. Yeah, I think that's right. So if you're wondering where this formula comes from, it's a formula for the sum of squares. It's n times n plus 1 times 2n plus 1 over 6. Though for such a small number, you can just compute it yourself if you don't know the formula.
So the next question asks for the median of this list of numbers. And one thing to note, this will also be very helpful this year. One very nice square to know is that 45 squared is equal to 2025. So you'll notice that what this means is that we have 44 squares that are less than 2020. So first of all, to find the median, we're looking for the number between that occupy the 2020th and 2021st places, and then we just take their average. And this tells us that we have 44 numbers that if we were to take a list that go before if we were just to take the list of 1 through 2020, we have 44 numbers that bump the list outwards. So if we were to just consider the numbers from 1 to 4040, our median would be 2020.5. But since we have 44 numbers that are bumping up this list from the bottom, as in we have 44 numbers that are, in addition, less than 2020, and we don't go beyond the 44 squared when we're going down 44 numbers because the distance between 45 squared and 44 squared is 89. This tells us that our new median is going to be 44 less than our original median if we were just counting from 1 to 4040. So this tells us that the answer is 2020.5 minus 44 is equal to 1976.5? Yes.
Yeah, that looks right. Yeah. Coded. So it's in coding it. I don't think they'll let you do it on the real test, but coding it. Yeah, that's an interesting thought. Also, I like how she mentioned that you should know 2025 squared. You should also know the prime factorization of 2022, which is very important. 2 times 3 times 3, 37. The number of times last year that they used 2021 is 43 times 47. I cannot count. It's absurd. But yeah, let's keep going. So we have problem 12. Triangle AMC is nice one. Triangle AMC is isosceles with AM equals AC. I don't think I realized that on the actual test. AMC.
Very impressive.
Medians MV and CU. So medians break down the opposite side into equal segments. Are perpendicular to each other. I did not draw that. And MV equals CU equals 12. So MV CU 12. Okay, 12. 12. What is the area of AMC? Okay, this is a very interesting question here. So we have isosceles triangles. That means I know that I have a lot of equal lengths here, right? I actually have sort of this isosceles trapezoid at the bottom, and if I actually take MCVU and I rotate it a little bit, I'll just redraw it right here. You can notice that after I draw this, like this, really, this is my new MCVU. And it's easier to do this on paper because you can just take your paper and spin it around. But this is really just 4 triangles, right? And we have UC equals 12, MV also equals 12. So you take the area of those triangles. You take 12 times 12 over 2, which is 72, which is going to be the sum of this entire quadrilateral because that's perpendicular diagonals like this. And so we know then, we also know that we're intersecting medians. So we have area of AUV is equal to 1/4 of area AMC, right? So this little triangle here has 1/4 the area of my big triangle AMC because it has half the side lengths and is a similar triangle. So we know that the rest of it, which is UVMC, is equal to 3/4 the area of AMC. And so we know that 72 equals 3/4 the area that I want. My area is going to be 96, which is answer choice C. There we go.
And
So
there
again,
was a question. There was a question in chat whether the 12 applies to, for example, all of VM or just the part up to the right angle, and it does apply to the whole segment.
It applies to segment MV. I'm sorry for like writing it like that, but there's like no place I could really denote that with unless I could use a different color actually, like something like this. Oh god, that makes it look worse. 12 from M all the way to V. So
Yeah. So the next question here is a frog question, which is very, very common on the AMCs. Something about the frogs. And this question is a probability question. So we have this coordinate grid, and we have a frog sitting at point 1, 2. And it does a sequence of jumps where each jump is parallel to a coordinate axis and moves by a unit distance. And this choice is IID. And the sequence ends when the frog reaches a side of the square, where the square is defined by these lines here. And the question asks, what is the probability that a sequence of jumps ends on a vertical side of the square? So we can do this with a little bit of symmetry, and considering what happens when we go in each direction from this point where we start. So the most obvious one is when we go left, we just bump straight into this left wall, and then we end our sequence. So with probability 1/4, which is the probability that we go left first, the probability that we end on a vertical wall is 1. Now we examine going to the right. And if we go to the right, then we'll end up in the middle. And you'll notice that the middle is symmetric with regards to whether you end up on the left, the right, up, or down at the end of your sequence of jumps. So because of this symmetry, we know that if we go to the middle, then the probability of ending up on a vertical side versus a horizontal side is 1/2. And similarly, if we go up or down, we will also end up on one of these main diagonals, which tells us that we have symmetry with regards to whether we end up on a vertical or horizontal side. So this gives us plus 2/4, which is the probability we go up or down, times 1/2. And then doing the math, which is non-trivial, 2/8 plus 1/8 plus 2/8 is 5/8, which is our answer, which is answer choice B.
Yeah, fun fact, that was my most hated question on the
Really?
entire test. Yeah,
This was
no,
my favorite question. The
no,
symmetry is so nice.
well, if it is if you realize it on the test. But I don't know. I just really don't like that one.
Are you
It
not
was
a fan of
this.
frogs?
I am not a fan of frogs. No,
Unfortunate.
very unfortunate. I think frogs. Anyway, I tried to do that problem with states and I did solve it, but it took like so long. And then I look back, and then after the test, I looked at the solution. I'm like, oh, So
That's fair.
state, yeah. With states, you label your center, your inner edge, and your inner corners. I think those are the three states. Let's go to question 14. So we have real numbers that satisfy x plus y equals 4, and we also know that xy is equal to -2. What is the value of x plus x cubed over y squared plus y cubed over x squared plus y? Okay, so I want to simplify this. I'm going to make some common denominators first. So um, I could combine my x with my y squared, but that'll give me an xy squared term. I don't like those terms. So I'm going to combine my x with my y cubed over x squared term and my x cubed over y squared with my y term. So I'm going to change colors real quick to show this. Combine these terms here to get x cubed over x squared plus y cubed over x squared. And I'm going to combine these terms here to get x cubed over y squared plus y cubed over x squared. No, y cubed over y squared. There we go. Let's move that up a little bit. And so then I can actually just combine my terms. So I have x cubed plus y cubed times, yeah. I have x cubed plus y cubed times a 1 over x squared. And then I have a 1 over y squared. And I'm trying to color code this, which is very slow. I should also put parentheses around the first x cubed plus y cubed. Wordplay. Goose always wins. What? Okay, I don't get that chat message. Anyway, I know x cubed plus y cubed can be factorized. X plus y times x squared minus xy plus y squared. Does this problem guarantee that x and y are integers? No, they could be complex numbers. I think they actually are complex numbers if you solve the quadratic that comes with it. Is it? No, it's not. No, they're not. 16, no. They're not. Okay, I'm not going to bother trying to solve it in my head. And then 1 over x squared plus 1 over y squared, I can also combine the fraction. So I get this on the top. Okay. Now I can use some of the things I already know. For example, I know that x plus y is just 4. So I want to write everything in terms of x plus y's and xy. So I can write x plus y is just x plus y. Then this term here, I can rewrite as x plus y squared minus 3xy. And then that up there, I can write as x plus y squared minus 2xy to cancel out the xy terms I get from this. Now it's just plug and chug. So I get 4. Here I have 4 squared minus 3 times -2. And then on the bottom, I have a 4, that's -2 squared. I have 4 squared minus 2 times -2. The number of parentheses I have makes me think I'm doing coding. For 16 plus 6, 16 plus 4 over 4 times 22 times 5, 20 times 22, 440, which turns out to be answer choice D.
And just to point out, you could actually find the values of x and y here, and they are relatively nice in that they are real, but they are irrational and ugly. So just like the big takeaway from this one is that when you have expressions that look kind of annoying to solve, don't solve them because there is probably a better way to do it that will save you a lot of time. AMC is not very considerate with the routes that they choose.
That's kind of the point, because if you could solve it without doing the algebraic manipulation, like what they're testing on is your ability to do that.
Mm.
If I'm not mistaken, these are the roots to that solution. So x will be 2 plus root 6, y is 2 minus root 6. Good luck taking the cube of that and then dividing. just saying.
All right, so our next question is, so we are choosing a random divisor of 12 factorial at random, and we are asked for the probability that the divisor chosen is a perfect square. So to do this, we find the total number of divisors of 12 factorial, and we find the number of divisors that are perfect squares. And this is going to be slightly bashy. Okay, so the number of divisors that are 2 is... Okay, well, the fast way to do this is you divide 12 by 2, and you get 6. And then you divide that by 2 again, and you get 3. Then you divide that by 2, and you get 1. And then that's it, because you can't divide 1 by 2 anymore. You take the floor each time. And then for 3, this is 4 plus 1, and 5, there's just 2 of them. And for 7, there's 1, and 11, there is another 1. So the total number of factors, we find this by adding 1 to each exponent and then multiplying those numbers together. So we get 11 times 6 times 3 times 2 times 2 as the total number of divisors. Now, to look for the divisors that are perfect squares, we just comprise each of these divisors out of perfect squares. So we have that our original factorization is 2 to the 10th times 3 to the 5th times 5 squared. These are actually irrelevant, these last two here, because if we try to include them in a perfect square, we will need to double up these factors, and we can't because we only have 1 of each, so we can just ignore these. And from here, we can only take even exponents if we want to have a perfect square. For example, 2 squared times 3 to the 4th is a perfect square, but 2 times 3 to the 4th is not. So this gives us some choices for the number of 2s, 3s, and 5s. We have 6 choices for the number of 2s, which goes from 0 to 10. And then for 3, we can do 0, 2, or 4. So that gives us 6, 3. And for 5, we can do either 0 or 2. So this is 2. So this is the total number of factors which are perfect squares. And finally, we can divide this by this number here. So we have 6 times 3 times 2 over 11 times 6 times 3 times 2 times 2, which is 1 over 22. And the problem asks for the sum of the numerator and denominator, which gives us 23, or answer choice E.
Very nice, yeah. And if you're wondering how like the trick of taking the floor each time works, I'm just gonna explain it really quickly here. So visually, you can see that like from 1 to 12, right? Some of the numbers have factor 2. For example, 4 has 2 factors of 2, 12 has 2 factors of 2, right? And you could count these vertically: 1 factor, 2 factor, 1 factor, 3 factor, 1 factor, 2 have factors, or we could count them horizontally. We'll have 6 factors, 3 factors, 1 factors. As you can see, hopefully each time I take divide by 2. And it's a similar thing for all the other prime factors like this. So that's how you get that little trick. But let's move on. Problem 16. A point is chosen at random within the square in a coordinate plane whose vertices, so we have a square from 0, 0, all the way to this is square, so 2020, 0, 0, 2020, 2020, 2020. That's horrible handwriting. Probability that a point is chosen within d units of a lattice point is 1/2. So basically, lattice point is every grid point in here. There's 21 of them in each row. What is d to the nearest 10th? Okay. So what basically happens is, with this question, is that I don't have to really consider edges. Like edges, you might argue that, well, it might. No, it doesn't have an effect because they only want d to the nearest 10th, and 2020 is so huge compared to a small lattice point that we could reasonably ignore any effects generated by the edges. I'm pretty sure they don't have an effect anyways, so nonetheless. Anyway, so I have 4 lattice points here, like this. They're all 1 apart from each other, so the probability that a point is chosen within d units of a lattice point, well, I have a circle with radius d, and then if a point is within one of these circles, then they are within d units of my lattice point. And I can actually chunk up my grid into a bunch of these squares. So like 20 squared of these squares, for example, right? Like that. And we can only consider one of these squares because, like I said, they're all identical. Each of these squares are identical. 20 is large enough. I don't have to worry about what happens near the edge. So you just have to consider what happens in one of these squares. Well, the area of the entire square is just 1. So we don't have to worry about my total area is 1, but the area of being in one of these 4 quadrants is pi times d squared. So I want d within d units of a lattice point is 1/2. Right, so pi d squared has to equal 1/2 because we're given this probability is 1/2. So d is equal to the square root of 1 over. Sorry, excuse me.
Bless you.
1 over 2 pi. And then that's the square root of about 6.2-ish. So actually, let's do this. So we know that, so I have to estimate this here, right? So I'm going to say d squared equals 1 over 2 pi, which is about 1 over 6, which is like really slightly smaller than 1/6, right? Which is, let's just call this about 0.16-ish, right? Because 1/6 is equal to 0.16 repeating. It's a little bit smaller. We're just saying that's 0.16, and that's really nice to take the square root of, so that's 0.4. And then we hope that we don't make a mistake. But that is the correct answer. Is answer choice B here. Again, AMCs don't let you have calculators, so this is kind of what you have to do for this.
So for the next question, we are given this polynomial up here, and we are asked to find for how many integers n this equation, this polynomial, evaluates to less than or equal to 0. So for this, we have to think about what plugging in numbers in different intervals does to the value of the polynomial and when it equals 0. So I've written out some intervals here. We are examining the intervals between roots. So we're starting at the most negative things that we can plug in, which is if you imagine the graph to the left of 1 squared, and then we're looking at from 1 squared to 2 squared, and then 2 squared to 3 squared, and so on. And we go all the way up to the very, very positive numbers. So we can examine this by thinking about how many terms in this product up here. We can think of this as a product essentially. How many terms are going to be positive and how many are negative? And you'll also notice here that I took the open intervals, which means we're not including the endpoints. And this is because the endpoints, so 1 squared, 2 squared, 100 squared, they make the polynomial evaluate to 0. So for this first interval, only the first, actually wait, on the first interval, this is positive because all of the terms are negative. And then as we transition to the second interval, we are making the first term here positive, but everything else is negative, which means we have an odd number of negative terms, which makes it evaluate as negative on this interval. And you may notice that as we continue to do this, the signs will keep switching because we are simply moving on to the next bracket and making it positive or negative. So from here, we are looking for the intervals where the expression evaluates to less than or equal to 0. The easiest part is to do the ones where it's equal to 0, which is just the roots. That's 1 squared, 2 squared, all the way up to 100 squared, which gives us 100 times where it's exactly equal to 0. And for everything else, we are looking at when it is negative. So these are the intervals where the lower bound is odd and the upper bound is even. So this is going to be our last interval. And the sizes of these intervals, they are exclusive. So we take the upper bound minus the lower bound minus 1. And then similarly, all the way up to 100 squared minus 99 squared minus 1. And this will be a sum of differences of squares. So we have 2 minus 1 times 2 plus 1, and then 4 minus 3 times 4 plus 3, all the way up to 100 minus 99 times 100 plus 99. And something you may note is that in all of these expressions, we have the difference of two consecutive numbers, which gives us just positive 1. So we have 3 plus 7 plus all the way up to 199. And we can find this sum using the sum of an arithmetic sequence. We take the first and the last term times the number of terms over 2. How many terms are in this sequence? 50? That sounds correct. Is it 50?
I think it is because you have 100 and then each was a
Yeah,
pair.
okay.
So
Yeah. So we evaluate this and then we add in these things that we found before, the 100 values where it equals to 0. So we end up with the sum of 5,000 plus 100 is equal to 5,100, which is answer choice E.
yeah, that's very nice problem there. Let me pull up the next question. Okay, question 18. So we have A, B, C, and D be an ordered quadruple of not necessarily distinct integers. So A, B, C, D. They could be the same integer. They don't really care. Such that A, D. So we have each of A, B, and C, D. I can pick between 0, 1, 2, or 3. Those are the only numbers I can pick from. And for how many of these quadruples do we have AB minus BC is odd, so it's 1 odd 2. And we just want to find how many of them there are. So really, we can divide this into two cases, both of which are equal to each other. We can either have AD be even, and then BC be odd, or we can have AD be odd, and then BC be even. And they're equivalent by symmetry, like they have the same number of quadruples that make them work. So we can only consider one case here, where AD is even, and then BC is odd, and then we write a very large 2x at the top of our scratch paper to remind us to multiply by 2 at our end of the calculations. You'd be surprised at how many times people forget to do that. So number of ways. So AD even means that one of A or D has to be even. So that's 12 ways. Then BC odd, that means both of them have to be odd. That's 2 times 2, which is 4 ways. And the way you can do it is you can start with odd, right? 2 times 2, that's 4 ways. Every other way makes the product even, which is 12 ways. So 12 times 4 is 48. We have to remember our 2 times up there. So 48 times 2 gets us 96 values, which is answer choice C. That looks like a copyright sign because I wrote the C really small. Yeah.
Kind of accurate.
Very accurate.
All right, so the next question is about this regular dodecahedron. This is also one of my favorite problems on the test. I'm a little biased, I like combinatorics. So,
This is one of my favorite problems because it's been blatantly stolen from a past Amy problem.
oh, really?
The Amy problem, it was like 2018, I think, or something like that. It was the number three. I think it's 2018 number three. I'll go check that. But it's they use instead of dodecahedron, they use an icosahedron, but you start at the vertices, I think, because that's 12 vertices. So yeah, dodecahedron, icosahedron, they have the edge vertice duality. So it's actually the exact same answer. If you recognize that, you can just circle in the answer and just move on.
Okay, well, let's pretend that we did not recognize that. So the problem is we are starting at the top face, right here, and we are trying to find a path all the way to the bottom face. And we can move from face to face. And so, for example, an example path could be you go like this, and then you go like this, and then you go here, and then you go down. So one of the conditions in this problem that is imposed is that you can't revisit the same vertex twice, and you can only move down. So once you exit this ring up here, down into the bottom ring, you can't go back to it. So this makes the problem significantly easier. If that was not the case, this would be a much harder problem. So our first step, yes, you can go sideways. So you can, essentially what this boils down to is you start from the top, you enter this top ring here. You can traverse the top ring in some way. And then you go to the bottom ring and you traverse it in some way. And then you go to the bottom side. So when you start at the top side, your first choice is which of the 5 sides in the top ring will you go to? So this gives us 5 choices. And now we are on one of the sides. Without loss of generality, let's assume that it's the front side. From here you have, well, you can stay on your top ring, right? And you have 9 ways to stay on your top ring and traverse it in some way. And how we get to this value is, so you have one option, which is you only visit this face that you picked originally. Or you can move in either the clockwise or the counterclockwise direction. And in each of these directions, you have 4 steps that you can take. So you can go 1 step, you can go 2 steps, which is somewhere back here, 3 steps, or 4 steps, which will land you on this side. So this gives us 9 ways to traverse the top ring. And after this, you go to the bottom ring and without loss of generality, let's assume that we traversed all the way around the top ring and now we're on this side. So wait, this is not the right without loss of generality for this example. Let's assume that we did not traverse the top ring. So we just stayed in the original side that we chose. From here, we have 2 ways to continue our path into the bottom ring. We can go to the left or to the right. So this gives us 2 choices. So we have 5 times 9 times 2, and you will notice that the bottom ring is completely symmetric to the top ring. That means you can traverse it in the same number of ways. So we multiply by 9 again for traversing the bottom ring. And then after that, we have no choices left. We just have to go to the very bottom face. So we multiply by 1. And this gives us the answer of multiplication. 81 times 10 is 810. And this is answer choice E.
All right, that's very cool. I found the problem. It's 2016 AB1 problem 3. If you guys are looking for it, it's the exact same answer. Let's keep going to the next question. So we have quadrilateral ABCD satisfies. We have a right angle at ABC, and then we have another right angle at ACD. So something like that. There we go. So A, B, C, D. We know that AC is equal to 20, CD is 30, and then we have diagonals AC and BD intersect at E. So we have something like that. E right there. So we know AC is equal to 20 And then we want the area of quadrilateral ABCD. Actually, there's one more piece of information that they give us. AE is equal to 5. So that means I didn't draw this to scale. You guys will just have to deal with it. Anyway, so A is equal to 5. And then I have another right angle down here. And when we want an area. So how can we start with this? Well, in AMC geometry questions, there will almost always be a similar triangle you can work with. And I see one where we can go, we drop an altitude like this. And since we know that AC is equal to 20, we know that EC is equal to 15. So CD to EC has a 2-to-1 ratio, which means it's going to be the same thing for AB down here. Let me move this. Oh god, I don't have space to draw anymore. I'm running into like areas that I've drawn before. So we're just gonna, okay, I'm gonna call this point F here. And so then I can just label this. So I have FE is going to be equal to X, and then BF is going to be equal to 2X. So right now, again, because we know the area of triangle ACD already, because we know AC and CD, we really only want the area of ABC. That's actually the challenge of this problem. But we also know that ABC is a right triangle like this, which means that my height actually splits into two other sets of similar triangles. ABF is similar to BFC. Let's see. What can I draw? That gives me space. This should work. Okay. So that means if I redraw my ABC triangle like this, something like this, and then I drop the altitude from, I'm not labeling this right. I draw the altitude down to F. I have 2X. This is 30. And I should be able to find some lengths like this. Can I? Yeah, I think I can because of similar triangles. Let's see. Let's see if this. Oh my god. I'm gonna draw. Okay, let's try this first. So we know that. Trying to think. So by similar triangles, I have 2x over CF is equal to AF over 2x. So this is AF times CF equals 2x, right? But we also know that, what else do we know? Well, we know that we have an E point here. This is 5. This is x. So AF is equal to 5 minus x. CF is equal to 15 plus x, because it's the other side. So 5 minus x times 15 plus x is equal to 4x squared. Oh my god, this is a mess. 15 minus x. All right, we're clear to that. So 5 minus x times 15 plus x. And I can just expand this. 75 minus 10x minus x squared equals 4x squared. 5x squared plus 10x minus 75 is equal to 0. X squared plus 2x minus 15 is equal to 0. It's pretty easy to factor that. X minus 5. X plus 5 times x minus 3 equals 0. Obviously, the length will not be negative 5 because actually we have to make sure of that because we know that F is to the left of E in the diagram, right? It won't be negative 5. It has to be positive 3. I'll be careful here. So x is equal to positive 3. And then going back to that, that means I know I have a triangle with height 6 and base 20. So the area of ABC is going to be equal to 60. And we already know the area of ACD is equal to 300. 30 times 20 over 2, 300, adding up 360, which is our answer choice D. So, It's actually one of the rougher geometry questions they throw on the AMC
Yeah, that one
channel.
was a struggle. I didn't like it very much because it's not obvious. If you drop a different altitude, it is much, much more difficult to solve. You just need to find the right altitude to drop.
Yeah, I think I solved that one with. I think I skipped that one.
I did
2
as
years. I
well.
think I took it like 3 years ago. There's another one with. I think like if I didn't see the altitude on this, because the main motivation behind that was there were similar triangles, but it could have just as easily been another set of similar triangles if we dropped this altitude here.
Mm.
Like these two triangles here are similar, and there could be another solution with that actually. But I wouldn't bother to do that right now. Let's just move on.
All right, so the next question is asking about this expression on the left, and in a slightly convoluted way, essentially it asks when we express this as a sum of powers of distinct powers of 2, how many terms are in the sum? And this uses one fact twice, which is the expansion of a geometric sequence when it is finite. So, first thing you might note is that we can actually break this down as a geometric sequence. This is a geometric sequence with first term 1 and the common ratio of negative 2 to the 17. So this gives us a sum of 2 to the 17 times 17 plus, oh wait, no, times 16 minus 2 to the 17 times 15 plus 2 to the 17 times 14 down to plus 1. And this looks good, but it's not good because we have negative signs and we need to make them all positive. So what we do from here is we consider pairwise sums. So let's examine this thing on the left here. 2 to the 17 times 16 minus 2 to the 17 times 15. We can factor out a 2 to the 17, and this gives us the difference of 2 to the 16 times minus. Something about this feels not correct.
I think it's right because
It is?
yeah, I think if you just expand that, you'll get a different powers and they won't overlap. That's how I did it at the test, and it's been a long time, so I don't remember. I think because then you can
Mm, yes.
wait no wait it's two to the 16th then to the 17th power, right?
Yes,
That's how
okay,
like
I
yeah,
see.
exponents
Yeah.
multiply. Yeah, I think it's the other way around. I think
Other way
you
around?
want them to both be the power to 17, so you can use the expansion again. I think like the general x and minus y in expansion.
So 2 to the 15 times 17 times 2 to the 17 minus 1. That
Well,
is,
wait, no,
no?
wait, no, wait. I'm not. No, we could just do you could do 2 to the 17 times 15 times 2 to the 17 minus 1, right?
Yeah.
Yeah,
Okay. So from here,
yeah.
we know how to expand this bottom thing here. This is just 2 to the 16 plus 2 to the 15 all the way down to plus 1. And so this gives us 17 terms each time we have this expansion. And one important thing to note is that they don't overlap, as in when we take two consecutive expansions, so this expansion here with the 16 and 15 will end before the one with the 14 and 13 starts. So we don't have any overlapping terms, which is good because these are supposed to be all unique powers. And from here, we have, if we pair each of these off, so we have 16 with 15, 14 with 13, all the way down to 3 with 2, 2 with 1, then we will have 8 pairs of things. And each of them has an expansion that has 17 terms. But we are not done, because we have this dangling 1 over here from the beginning that was not counted in any pair. So we have to add this 1 back in to count the number of terms. And this gives us 136 plus 1 is 137. And this is answer choice C.
This is like one of the problems that's like always like harder to actually understand what they're asking for than, sometimes to solve it. But like as a general rule of thumb for like the last 5 questions, the easier a question looks or like the simpler a question looks, the harder it will be as a general rule because they give you less information. I remember like one particularly nasty number 25 that just looks super simple, but like the reasoning behind the way you have to look at it is super hard. Speaking of that, let's go to the next question, um, which has some pretty scary notation as well with floor functions. So we are given an expression of 998 over n plus 999 over n plus 1000 over n. And if you don't remember, floor functions act such that I take the integer part or like the greatest integer less than it. So for example, the floor of pi is equal to 3, the floor of 10 is equal to 10, the floor of e is equal to 2, etc. Something like that. So, and we want for how many integers in less than 1000 or equal to, this is not divisible by 3. So this is not divisible by 3. So now, let's say you're solving this question and you have no idea where to begin. Well, the natural thing to do is to list out some values of n and see what happens. Just quickly see if you can deduce a pattern, something like that, right? Because floor functions typically pretty hard to work with. So n equals 1, well, I have 998 plus 999 plus 1000. That's divisible by 3. That doesn't work. N equals 2, well, I have 449 plus 499 plus 499 plus 500. Well, that works. That works for 1. Then we have n equals 3. Well, that's like 332 plus 333 plus 333, right? N equals 4. So none of these so far are being divisible by 3, but we have to notice why. Mostly because we have a 1 difference here, going from 499 to 500, or 332 to 333, or maybe in this case, going from 249 to 250, right? And so what we can notice is that, well, since 998 to 1000 are so close to each other, right, what we can notice is that at most they will have a difference of 1 between them. They can't have more than the difference of 1 because their space between them is only 2 at most. My space between is only 2. So if I want to have a space where I divide by n, I want a space of more than 1. That's impossible, right? Because like 7 and 14, they're spaced by 7. But 998, is that making sense? Like they're only spaced apart by 2, so I can't fit like 2 multiples of a number in here, in that space. That's really the idea. You can see like with the pattern here, for example, because 1 is an exception, right? But everything else, at most, they differ by 1. So with that, we can notice that the only way for them to be divisible by 3 is if all of the numbers themselves are equal. So for example, if I take 7, right? 7, that's going to be 142 plus 142 plus 142. That's divisible by 3. But in what cases will I have a difference between them is when I have a multiple. Like if I place them, like if it's divisible by 999, right? Then I'll have 999 over n minus 1, 99 over n, 999 over n. And if it's divisible by 1000, we'll have 1000 over n minus 1, 1000 over n minus 1, and then 1000 over n. And those are the only cases where my number n is not divisible by 1,000. Yeah, you can see in these cases, right? 2 is a factor of 1,000, so it jumps up once it reaches 1,000. 4 is a multiple of 1,000, so it jumps up when it reaches 1,000. 3 is a multiple of 999, it jumps up when it reaches 999. I'm probably explaining this really badly, but that's sort of my reasoning when it comes to this. So we just number of factors in 999 and then number of factors in 1,000. We also know that 999 and 1,000 are relatively prime, meaning they don't share factors, meaning I can just find the number of factors, add them, and I don't have to worry about overlap. So 999 is 27 times 37, so 3 cubed times 37. So that brings me 4 times 2 equals 8 factors. And then this is 2 cubed times 5 cubed. 1 is an exception, right? Like I said, 1 is an exception, but it's only one case, so we can just deal with it at the end. That's 16 possible factors. So that brings me to 24, but there is a common factor here of 1, so I have to subtract that off. But then we also know that 1 actually makes it divisible by 3, so I have to subtract 1 off this again, because I don't want 1 in my count at all, so I have to subtract another 1, which brings me to 22. This is a problem you probably want to skip. There are easier problems in the final 5 for the AMC 10. So the worst part is the answer choices are 22, 23, 24, 25, 26 for the answer choices. So you could spend all of this work, and if you don't subtract this 1, you get 0 points. If you skipped it, you get 1.5. So it's something to watch out for.
Luckily, the next problem is actually much simpler than the previous problem. I think this one was slightly misplaced. So we have a triangle. The only important thing to note about this triangle is that it's like on the axes and it's not symmetrical about x equals y. So we have a triangle and we have a set of transformations. So these transformations are a rotation of 90 degrees counterclockwise, 180 degrees, 270 degrees, or flipping across the x or the y axis. And so these are 5 different transformations that we can do, and we're asked of the 125 possible sequences of transformations comprising of these 3 types of transformations, which will return this triangle back to its original position. So the biggest insight here is that we have to have an even number of reflections. And the reason why this is the case is that if we have an odd number of reflections, we change the orientation of the triangle. Because this triangle is not symmetric about x equals y, when we flip it, we get a triangle like this, and no amount of rotations will bring this back to this triangle. So we have 2 cases from here. If we have 3 different transformations in our sequence, and we have an even number of flips, we can examine having either 0 flips or 2 flips. So when we have 0 reflections, we need our rotations to add up to 360 degrees. So we can do this by, let's see, we can do 90, 90, and 180. Are there any other ones we can do? 270, 270, and 180. And we can do 180, 180, wait, no. Wait, that doesn't work. Okay. I believe, oh, and we can also do a combination of 90, no, I think this is it, right?
For like rotations? Yeah, I think so.
Yeah,
That's
yeah.
it.
Up to permutations. So within these rotations, we can rearrange them in any order. So this gives us a total of 6 for this case. Now, when we have 2 reflections, we can consider the two different types of reflections. So we can reflect about the same axis twice, which brings us back to the original triangle, but then we don't have a rotation to deal with that. Any rotation will displace it to a different quadrant, so that's bad. So that means that we have to have two distinct reflections. We have to have one reflection about the x-axis and one reflection about the y-axis. And when we do a reflection about the x and the y, we will end up with our triangle right here under a 180-degree rotation. So this means that the only thing we can do to bring it back is a 180-degree rotation. And this case gives us 6. We can permute this in 6 different ways. And adding up our two cases, we get that the answer is 12, which is answer choice A.
Yeah, that's right. I would like to point out that on the AOPS wiki, there is a solution that uses group 3, but the solution is identical to this solution, but only with different notation. So group 3 doesn't actually bring anything new to the table, which I think is funny, because it kind of highlights how people will do stuff like that. I don't know. Yeah, I thought of that because I was like trying to learn it like real recently, but it doesn't really matter in this context. But anyway, we only have 2 questions left, which is really nice. And technically, we will have to turn in our test right now because it's 1:16 Pacific time. But let's keep going anyway. So we have the least n be the least positive integer greater than 1,000. So n greater than 1,000, such that GCD of 63 n plus 120 is equal to 21, and then GCD of n plus 63 and 120 is equal to 60. We want the sum of the digits of n. Fun fact, on the AOPS wiki, this has a whopping 17 different solutions. Mine probably fits in one. We'll see what happens. So we know that n plus 120 is going to be divisible by 21. And we also know that 60 is divides n plus 63. But we also know that n plus 20 cannot divide 63, and then 120 cannot, because otherwise the GCDs will be larger than 21 or 60. So these are basically my conditions if I take them out of GCD format. So what I have then is I have, if I look at this relation that says n is congruent to -6 mod 21, because I know 126 is divisible by 21, and that this is n is congruent to a -3 mod 60. So, but then we also know that n cannot be congruent to -6 mod 63. Okay, we won't worry about those conditions for now. So now I have 2 of these relations, and I'm supposed to combine them in a number that is greater than 1,000. So the way I like to do this is I like to, the trick is you have to want to always start with the larger number. If you do casework on the larger number, you have less cases to deal with because the gap between them is larger. So, so I'm going to start with small numbers, right? So we know that n is going to be congruent to something modulo the least common multiple between these two, which is 420, I think. Yeah. So anyway, so like this cycle of how does it n will work repeats every 420 because I got a subcycle of 21 and a subcycle of 60 that work together. And I know that one of these will exist. First, I know that one of these will exist because there's an answer to this question, first of all. But the other reason is because I can actually simplify. So this is 2 mod 7. This is 1 mod 20 if I take out the 3's, right? And the 7 and 20 themselves are relatively prime. So by Chinese remainder theorem, there will be a solution to this system. This will be something you have to probably justify like in the proof or something, but not here. I just wanted to point it out. Anyway, let's test some values. So it could be 57, which is -3 mod 60, but it's not -6 mod 21, because if I add 6, no, it is mod, it is, yeah, it works, right? Does this work? It works. Yes? Yes? No? Yeah. 57 plus 6 is 63, right? So n is congruent to 57 modulo 420, and I know that that's the only solution that exists because 420 is the least common multiple between the two. Does that look right? I need to check this work. I think that's right, right? I'm like losing confidence in this, right? Like, by the second. I'm okay. 117 plus 6, and then 1.
Wait,
Is that right?
57 is not -6 mod, or 57 mod 420 is not -6 mod 21, right?
It is though, right? Because 63 is a multiple of 21, right?
Wait, but 420 is a multiple of 21. Oh, wait, yeah, okay.
Yeah, it's
Yeah,
supposed to be
you're
because
fine.
there's like cycles, right? Because that
Yeah.
cycles of 21 cycles of 60. 7 cycles of 60, 20 cycles of 21. There, so it's the least common multiple, right? And then so it's 50. Yeah, yeah. So then we just have to go to the smallest multiple that actually works. So we go, could be 420 plus 57, that's too small. 840 plus 57, that's also too small. 1320, no, that's not right. What am I doing? 1260 plus 57. But we have to, that gets me a number. But I have to check it against the conditions that are not allowed, actually, because I know that it can't be divisible with 63 or 120 like that. So it's probably a better way to do this. What does this get me? So I take this and I add it to, what's the question? I add it to 120. So 1 plus 60 plus 57 plus 120. Taking that mod 63. Um, Okay, what's the best way to do this? This is -6. This is -6. This is 0. So that's -12. So that satisfies that condition. And then 1260 plus 57 plus 63 mod 120. This is 120. This is mod 60. So it works. It works. It works. So this is a number that does work. Nullify one of the solutions. But 1260 plus 57 does it
Wait,
work?
are you sure your initial conditions are correct?
Yeah, yeah. I might have done something.
You got that n should be -6 mod 21, right? That is, I don't think that's correct. I think it should be +6 mod 21.
Oh, wait, is it? Is it? Yeah, what? Wait, is it? This should be positive, right? This should be positive, right? Negative. No, this should be negative. This should be positive. Yeah, okay. Oh my god. Okay, time to redo every calculation in here. This is great. I'm having a fun time. But at least, okay, n congruent to 6 mod 21, n congruent to, I forgot. 3, -3 mod 60. Is that right? Yeah, okay, that's right. I just have to plug. So 57 doesn't work. 117 doesn't work because that's -3, -6. So I have to multiply this by 5. 285. No, 290, 297 should work because. Is that right? Minus 297 minus what? I'm confusing myself now. 177. That's divided by 21. What's the next multiple? 160, 168. So that's in 9. Okay, wait. 168. Yeah, because this is a remainder of 9 mod 21. -3 mod. Is this right? Can you check that this is right for me, please? Just, I don't want to
Sure.
mess this up again. 177 over 21. Okay, link. It's possible. And then 237, because I want 6 mod 21, right? So this will work. This is 6 mod 21.
Yes, this works.
Yeah, that works. That works. Okay, 237. So that's 237 mod 420. And then it can't be, so it has to be 13. So it can be 840 plus 237, which is 1077. And I have to test against both conditions if this works or not. I feel like there's a way better way of doing this.
Well, I think we're multiplying by relatively small numbers, right? So there is a faster and more orderly way to do it, but when we're working with such small numbers, it is like not worth it.
Faster way. Do I have to check every one of these? Is there a faster way to do this?
Yeah, like you can set up a system of equations and reduce them with the modulus that you're working in, and then you can get conditions on the variables that you're working with.
I could, okay, yeah, I could do the thing where okay, let's do this. So 237 mod 420. I can write this as 420k plus 237 for some integer k, and that has to satisfy a set of conditions. So I take this mod 63. Oh my god, what is that chat message? If I take one of my conditions, so it can't be in. Oh my god. This is sometimes using online drawing is nice. Sometimes it's just a pain because normally like scratch paper would on the other side. I take this mod 63. It cannot be. I'm losing my train of thought. Cannot be equal to. Jesus.
We know that it's not divisible by 3, right? Otherwise the GCD would not be 21. It would be 63. So this tells us something about the variable that we're using.
Yeah, I know that. I know that because I just need to get the module. I keep forgetting what my modular condition for this should be. So it can't be divisible by 60 because when I take n plus 120 and then divide that by 21, it can't be divisible by 3. So maybe I should actually do that first because that will simplify things a lot. Why is this 237? Is this? It's not even right. Right? No? So I take 420k plus 237 and add that to 120. And when I divide that by 21, it cannot be divisible by 3 again, is what the problem is basically trying to say. 420k plus 357. Is that going to give me a whole number divided by 21? 117. Yeah, 17. Right? Yeah, there's 17. That cannot be divisible by 3, so 2k plus, what is this, 2? K cannot be 2 mod 3. And then for the other condition, 420k plus 237 plus 63 cannot be divisible by 120. Which means when I take this and divide it by 60, cannot be divisible by 2, so k cannot be 1 mod 2. So I have k cannot be 2 mod 3, cannot be 1 mod 2, which means that k has to equal 4 is the smallest one that works, should be. So that's 1680 plus 237, 1917. Okay, 1917, that's 18 as a sum. And I'm done. Oh boy. Okay, just make sure, like, there's a couple of key ideas here. I messed up badly on the writing of these conditions. Um, but the idea is that instead of working with modulo, you can write it in terms of an integer expression. That really works good, really works well, especially if you're trying to take powers of things. For example, this is going a bit off on a tangent, but if I have like a number like n is congruent to 1 mod 7, right? And I want to find n such that, like I want to find a power. The smallest power into the a is going to be 1 mod 7 squared. What I would do actually is I'll write n as equal to 7k plus 1, then take 7k plus 1 to a power, right? And then you can use binomial theorem, for example. That's like a trick that you can use for these questions. Yeah. So sorry about that. Anyway.
Okay, the next question. Probably just about as annoying as the previous question. This one is not fun. I don't know why it's on the test. So the question asked is, there's this kid named Jason, and he rolls 3 standard 6-sided dice, and he looks at the rolls, and if he doesn't like them, then he chooses a subset of them. So he can choose from 0 to 3 of the dice to re-roll. And after he re-rolls, he wins if and only if the sum of the numbers face up is exactly 7. And he is trying to optimize his chance of winning. The question posed is, what is the probability that he chooses to re-roll exactly 2 of the dice? So for this, the first step is to understand which strategy is optimal when, as in when do we want to re-roll 0 dice, 1 dice, 2, or 3. And so the first one is easy, right? We re-roll 0 dice if the sum of the dice is exactly 7. And the probability of winning in this case is always 1. Now, we re-roll 2 dice, or I guess we can go to 1 die first. We re-roll 1 die, I think when the sum of the other 2 dice is anywhere from 2 to 6, then on our die that we're re-rolling, we can have a 1/6 probability of rolling the number that completes the sum to 7. So this is if the sum on the other 2 dice is from 2 to 6, then in each case you have a 1/6 chance of rolling the one that adds in. So the question is in chat, what about 1? Well, 2 dice can't have a sum of 1 because each one displays at least a value of 1. Now, how about re-rolling 2 dice, which is what this problem asks for? Well, clearly I messed up in my notation somewhere. Re-rolling 0 has a 1 chance of probability of winning, and if you are forced to re-roll 1, then you have a 1/6 chance of winning from there in optimal strategy. For re-rolling 2 dice, this is significantly more annoying. So essentially we have to do cases by what the third die that we're not re-rolling, the value that is shown on that die. So do I need to make a table for this? Okay. So when the remaining die is 1, then the sum that you need for the other 2 dice is 6. And the number of ways to do this is you can have 1, 5, 2, 4, 3, 3, and then vice versa for all of them except for 3, 3. So this is a 5 out of 36 chance. And then if the remaining die is 2, then you have a sum of 5, which can be done in 4 ways. And then for 3, you have 4, which is 3 out of 36. For 4, you have a sum of 3, which is 2 out of 36 ways. And for a sum of 2, you have 1 out of 36 ways. So one thing to note here is that the best case where we are left with a 1, the maximum probability of winning is 5 over 36, and 5 over 36 is less than 1 over 6, as in when we can re-roll 1 die instead of re-rolling 2, we prefer that. So that's the only takeaway essentially from this entire thing. And then lastly, we can examine when we re-roll 3 dice, and in all of these cases, the probability of winning is we just find the probability of getting a sum of 7, which we can do quickly by stars and bars. With stars and bars, the ways of partitioning 7 into a sum of 3 terms where each one is at least 1 is 6 choose 2. And the total number of ways to roll 3 dice is 216. So this simplifies to 15 over 216 is 5 over 72. And you may note that this is worse than this, is worse than this, is worse than that. So in short, when we can re-roll 0 dice, we prefer that. And then when we can re-roll 1 die, we prefer this, and then 2 dice, and then 3 dice. So what is our conclusion here? Oh, well, this is actually not completely true, because some of these probabilities in here are lower than 5 over 72. Well, this is 10 over 72, this is 8, and this is 6. For these ones, this is 4 and 2, which is less than 5 over 72. So what this tells us is if when we pick 2 dice, we are left with a 4 or a 5. I also completely missed 6. But this
Well,
is trivial because there's no way to form a sum of 1.
Is
So
your probability for 3 dice?
For 3 dice?
Yeah, I might just be going crazy, but okay. Yeah.
Yeah. So what this tells us is when we pick 2 dice out of the dice that we rolled, and we're left with a 4 or a 5 that we're not re-rolling, this is actually worse than re-rolling all of the dice. So what we are looking for is the number of ways to do this, as in the number of ways where we can roll 3 dice, and when we pick 2 of them, have 1, 2, or 3 left over, but we also have to be careful of this first case. This is a lot to keep track of. What do we do from here?
I think the idea, general idea of this problem is that like because if it is possible, like here, like example here, like if I start with roll 2, 4, and a 5, right? I could re-roll my 5, and if it turns into a 1, then I can do it. And if that's possible, I will always roll 1 dice. But in the case of something like 2, 4, and 6, each of my no, or sorry, 2, 5, and 6, each of my pairwise sums are 7 or more, and that's why we can't do the 1. But so we have to re-roll 2 dice. But so the idea is that one of my dice has to be from 1 to 3, but my pairwise sums are all greater than 7. So that's 2 like conditions that's pushing down here. So I think it's actually easiest to just list out cases from here. So like my smallest dice is 1, right? But I want all pairwise sums to be 6 or more, so it has to be 6 and 6. If anything is less than 6, I have a sum of 6 that I can re-roll 1 dice. Then from 2, right, 2 can go 5, 6, 5, 5, or 6, 5. And actually, these two are equivalent, actually. So the way I like to count like this for stuff is going from smallest duplicates, so 5, 5, 5, 6, excluding duplicates. Then for my smallest dice of 3, well, I could go 3, 4, 4. Well, I can't have 3, 3. Yeah, I have 3, 4, 4, 3, 4, 5, 4, 6, 5, 5, 5, 6, and then 6, 6 near the bottom.
Is there a reason you excluded 6, 6 in the 2 case?
The reason is I forgot it.
Okay.
Thank you for reminding me. Okay, so how many ways? So that's three ways, 6 ways, 3 ways, 3 ways, 6 ways, 6 ways, 3 ways, 6 ways, 3 ways. Looks right to me. Um, and because I need to have at least one dice from 1 to 3, as you showed us, as she showed us. So we have 12. That's another 12. That's 9. That's 9. That's 42 over 216. 7 over 36. So there's the answer. Sometimes it's just easier to just give up and start listing stuff. Oh boy.
That was the 2020 AMC 10A.
Man. Yeah, no. That's
Those last 5 problems really take you down.
it's yeah, it's mostly I don't know. I feel like if we had like actual scratch paper to do this on, what we would I don't know. Are we going to see Professor Lowe? No, he's not here today. Sadly.
Very, very
He's
rude.
he's actually at BMT, whatever college math tournament I think, to give you a talk. So that's why. Um, but yeah. So wow. I don't know. There's just a lot of things in like the last few questions are always going to be time consuming. Like I
Mm,
always like to try to reach the last five with like 30 minutes left. That's like typically my goal.
mhm.
Um, but even then, that's a lot of times not enough. Especially for
It also goes to show like the value of looking through the last 5 questions and picking out which ones are the most doable because a lot of them are very time consuming, right? So you have to, if you pick one of them, you have to dedicate a lot of time to it. So you have to like look through them. You have time to spare essentially in choosing which problems you do because that will significantly reduce the amount of time you spend actually working on the problems. And another good thing to note here is if you remember, I think it was problem 23, that one was not difficult. And it was placed in the last 5. So that just goes to show the value of looking through them once you get there.
yeah, and the other thing is like I really like that point. Like I almost forgot to bring it up, but like I always like read the last five questions once I get to them, like all five back to back. It's a similar thing on the AB once you get to like the last five on the AB. Um, the other thing is like because 23 was misplaced, it was really easy, but then 13, for example, would be a problem that I will skip. It's just I look at it and I start doing stats like no, no, no. I think I skipped it when I actually took it in eighth grade. Especially on like the AMC 12, which I know a lot of you aren't taking, but like the AMC 12 is like a way more buffed up version of the AMC 10. So especially for their last five questions, like you really just got to pick two or three to target sometimes.
And there's a lot of value to knowing your strengths and knowing where you can save time by skipping. Like for example, if you do come across a problem, that's like relatively early on, but you know that you will struggle with it. Knowing when to skip is very, very good because you might be trading off, say, problem 13 for something like problem 23 later on. So just like being cognizant that skipping can be a good thing and like making sure that you are strategizing to maximize the amount of time you spend solving problems, that comes in very handy, especially with the later AMC 10s where they sort of I think they've gone on a trend for going for like more punchy problems earlier on. So in those cases, it is a good idea to evaluate your like expected value of solving a problem for each problem that you do and figuring out when you should, dedicate your energy to solving that one or look through more problems and see which ones you can do.
Yeah, which is harder, AMC 10 or AMC 12? AMC 12 by definition. AMC 12 has like a lot of like AMC 10 problems, but they're always placed earlier. Like the 25 that we did is 23 in the AMC 12. AMC 12 also has harder concepts. It has trigonometry, complex numbers, and then just more difficult things with polynomials, and that's like the biggest difference. I can't take the AMC 10 anymore. I have to take the AMC 12. Why? Because like it's 4 days before the test, we're just giving out competition advice. The other thing I like to mention is that when you do skip, you always want to, almost always, you want to leave it blank. Here's why. So if you guess randomly, let's just assume random, you have a 1/5 probability of getting it right and getting 6 points. And you have a 4/5 probability of getting it wrong and getting 0 points. That's an average of 1.2 points as your expected value. But if you skip, you're guaranteed a 1.5 boost. So that's why you do usually want to skip, unless if it's like a 50-50 and that sort of stuff. Or if you're lucky enough to have solved 25, if you're lucky enough to have solved 24 of the problems and you're just left with one, you could just guess that one. I mean, you go for glory and the 150, but that never happened to me. The
In the
other thing,
hypothetical world where this
in the
happens, go
hypothetical
guess.
world, I mean, it's yeah, I think I did that last year, but I didn't guess right, so
Oh,
144.5 it is for me. Um, the other thing is when you should start checking your answers. It really depends where you want to start because silly mistakes is just the worst feeling ever. When you read a question and then there's really a few types of silly mistakes. The first type is ones where you get it early on, right? You get it early on, and you start going through like the algebra, you start crunching the numbers, and something doesn't feel right. And then you have to look back to your scratch paper, and then you have to find the mistake. And once you find the mistake, you have to do the question all over again. That wastes so much time, right? But then you have like the mistakes, like question what was it? Question that was mine with problem 24. You guys saw that entire process, right? But then there's also questions where the answer choices are super close together. Like which one was it? Which one was it? The 22, 23, 24, 25, 26 one. Problem 22, right? You
mhm.
mistake one, and then that's just 6 points down the drain. So for those types of silly mistakes, I usually start to check my answers about 15 minutes before the end. It's always a good idea to like bring in some sort of timekeeper like for the actual test. Hopefully they will seat you near a clock. Um, 15 minutes and like for like checking silly mistakes, a lot of times it could be just your very last step. A lot of times silly mistakes happen in the last step because if they're not in the last step, you would notice them earlier. The Amy last year, I silly 3 problems this way on the Amy, which is 30 points just gone. because and all 3 of them were just computation errors at the very last step. And Amy is short answer, not multiple choice, so you can't use the answer choices. Um, but yeah, which was fun.
This is actually
Was
very interesting to me because I don't go back and check. For me, I don't have enough time. Like, I don't solve through all the problems. So when I do my solving, I just like do my solutions with accuracy in mind as opposed to speed. And I think for me, that saves me time because to have to go back and to like reframe your mindset into that previous problem, like take time to go through your solution again. I feel like that adds more time to me than just like going through it accurately the first time.
Well, I usually like to flag problems that like are syllable by nature. Like for example, like if you have a question what like some what was an example here? We could do like the 7 cubes problem, right? 7 cubes problem. That's not something that can be easily silly because we do make a computation error, you're gonna notice it. So I just don't go back and check that. But then for questions like problem 11, the median of the numbers, I would flag that. I would go back and make sure I did that correctly. But it always depends on like how close I am to solving the last 5 questions. Like if I have question 24 that looks like I can solve it, I might cut out some like extra time at the end to go check that. Because again, 75 minutes is not a lot of time. It's really short. Um, but yeah, I don't really know what else to say for sillies. The other thing is keep your scratch paper really organized. Like problem 24 for me when I was solving this, we have like bit paper, like we have like a tiny window to draw, and we would have to move to somewhere else. I have to like actually move the screen, the drawing area around, so I can't see what the other stuff is. But the neater your scratch paper is, the easier it is for you to spot mistakes, and also the harder it is to make mistakes. Like a lot of times, like sometimes we're like not careful with writing things. Like you mistake things for other things, and you don't notice that. Um, Always, I've read this before, but I like to just box in like solutions for like my scratch paper. I would like if my drawing pad, like if this is my scratch paper, right? What I do is I cut off a section, right? And that's for where I write down my answers. Because online testing, right, there is a very real chance that you click a different answer than you actually get. I write those down. Then if I solve question one, like this, I then box that off, and then question two, and so on. So it's easy to flip back and see where you actually solve those instead of solving those again. Um,
Yeah, organization is a very, very good idea. Another good idea is writing so you can actually read your own handwriting accurately. Like
right.
there are too many times where I've written a seven and it's been a one. So I've changed my handwriting so that sevens look like this. Um, Other things, when you write signs, make sure you like read it after. If you have a plus sign, it's not a minus sign. And when you have a minus sign, that's not a plus sign. I think sometimes we forget that. It doesn't
It's
end up good.
especially like never ever ever do this. If I have expression, if I write down like 7 plus x, then I realize it's 7 minus x, do not just do this. Okay? You coming back in an hour will have no idea what that's supposed to be. Just cross it out and do 7 minus x. Um, Other thing is when you're writing exponents, there is a very real chance that if you're writing really too fast, x squared, um, y could turn like x times, you could think of it as x times 2y if you write that badly enough. Um, or like the thing with fours and nines. I That's why I write fours like this. People get mad about it, but then they mess up on the problem, and then who's laughing now? Um, what else? Sometimes I've had moments where I've just looked at like a multiplication algorithm and then just started doing this, which is not good. It's like things like that that happen. Um, or when writing sums, for example, um, or Venn diagram problems sometimes. I think this is a really, really common mistake to make. And it goes back to the problem 8, the one where they had you find the sum. Like this question, if you guys remember this one, right? A lot of people would subtract one copy of 4 plus 8 plus all the way to 200, but you have to subtract two copies. That's like one of the super common silly mistakes to make.
Another one is
Um,
like off by one errors, or like you forget to add on one term. The one problem with the 2 to the 17 whatever, there was that extra little one that like there were two answer choices that differed by one, and if you didn't add that one, you would have gotten the wrong answer. So just like really making sure that you're including everything in your expressions and you're not missing any like very trivial cases. That is very, very important, and AMC really likes to trip you up on that.
They do. Sometimes they put like really evil answers. The other thing is problem 11. You got 1974.5, 1975.5, 1976.5, 1977.5. There's also the reverse movement not being included. Yeah, that's referring to the other problem. Something else I wanted to say. Another thing I want you guys just to remember is cosine alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. Just wanted to. That's another source of sleep mistakes. Um, the other thing is signs error, like you mentioned as well. Because these are the easiest points to just lose on the AMC. Like you
Mm.
could spend a year learning concepts, or you could spend 2 hours practicing legible handwriting and get the same boosted score. So, um,
So it's a very worthy investment. It's just like things like, I think generally when we get into the competition mindset, our minds go a lot faster than like we can write or put things down on paper. And that causes a lot of times where there's like a disconnect that results in a silly mistake on the paper. So like you're thinking about something like 1.5 steps forward, but you're still writing the previous step down. And that results in things like the sign errors or like writing a different number than what you like wanted to write because you're thinking too fast. And so it's like it's a really conscious effort when you're in a problem solving mode and when you're trying to go fast to also remember that you have to slow down a little bit to make sure that you're preventing mistakes that occur from desynchronizing what you're doing physically with your like mental capacity to actually solve the problem.
Right, yeah, especially for like combinatorics problems and casework. Like if you see, remember like the last problem that we did, right? There's a very specific way to do this casework. You always want to make sure that it's systematic and it's always going to be count everything exactly once, not more than once, not less than once, unless you're intending for that. Like 1, 6, 6. Note that I order first off by I order everything from least to greatest, right? And then I can count permutations later. If I don't do that and I start doing it in a random order, I might write 166 somewhere else. I write 616. I don't notice. I count this as three ways. I count this as three. Bam! I get a wrong answer, right? Um, then you know, then I have a two and then a three case, and I always have to make sure because combinatorics are the easiest way to get off by one errors, and it's always super scary. Um, the other thing I have to mention is sometimes there was a problem last year on the 2021 fall AMC. Ilya, do you remember this one? It was the one where you had the guy rowing down a river with the current and then coming back against the current, but they didn't give you any distances.
Mm. Okay, I remember this problem happening, and I remember skipping over it, so I don't remember which one it was.
Let me see let me pull that up. Just fall 10A, I think. Um, Emily sees a ship traveling at a constant speed along the straight section of the river. She walks parallel to the riverbank at a uniform rate. Oh, it's the steps question. I
Oh no, no, it's that
put
one.
put the wrong answer at first, went back, redid it, and then got it right. The trick was I just had to write everything down, like every little detail, like her speed, the ship speed, the river speed, their speeds combined, her step length, everything. You just have to sometimes you just have to do that, especially a lot of things can be reasoned and some things just can't be reasoned. And this is at least for me, it's too complicated to keep track of.
Mhm. Another thing
Um,
generally is like taking a moment to think when you see a problem. I think when we are solving against time, we have a tendency to just like want to do things right away, right? Like you see a problem and you're like, okay, I see like one way to do this. And then you just go for it because thinking takes time. And when you are thinking, it feels inactive. And then that's like supposedly bad. But you could think of a better way to do it that saves you all of those like 5 seconds of thinking time by like a significant amount. So for example, for the dice problem that we just did, there you had to like think about what you wanted to do with this problem, right? Like think about how to break down your cases into like actually finding what you want to find. So there's a lot of planning that goes into solving problems, especially the last 5 problems on a test. And it's very valuable to, when you read a problem, process it. And actually, the first important part is to not misread the problem. Reading skills are very, very important. And when we do things under time pressure, sometimes we are illiterate, and that is not good.
oh
Generally, it's
man,
good to
tell,
read
tell
the
me about
problem.
it. Yeah.
But once you do read it, just like processing it and thinking before you start doing, even if it's for just a couple seconds, can really reduce and optimize the way that you do the problem.
Yeah. Do you guys have any other questions about like test taking strategies and stuff like that? One thing I think with the illiterate thing is I like to underline stuff that's really important, especially read the question, read what they are asking you for. Question four, for example, I don't know if you guys anyone noticed, but I blank because I thought I gotten the wrong answer when in reality they just wanted pay per hour and not total pay for that trip. Thankfully, there was the answer choices there, but that's what I'm saying. Sometimes have to read the question over and over again.
Sometimes you
Um,
have to read the question is just a good takeaway.
so they just have to read the question. Yeah, that's yeah. And then for like the nerves thing, because I know this ties into like nerves a lot as well. Um, I I can't really say anything about that other than just take more tests because like the more high stress tests you take, the better you get at just dealing with it. Um,
Well,
but yeah,
there's also the confidence of preparedness, right? Like when you go into a test, especially this is a good thing since we are so close to when the AMC actually is. It's a good idea to think about what you're doing in the last couple of days leading up to the AMC. There is sometimes like a want to do as many things as you can in the days leading up to it, right? Like some people want to start cramming tests in the last couple of days or review every problem they've ever done. And while this may benefit you to some degree, at this point, you're just about as prepared as you will be for the test, which means that what you really should be doing is instead of optimizing like the last bit of extra knowledge for the test, what you should be optimizing is the state that you're in when you are about to take your test. So what this means is you should not be staying up until 3 a.m. trying to cram your tests. You should instead use that time for sleeping, which is something we tend to forget. Or other things like the day before the test. Maybe it is not very good for you to take a practice test and fail it and go into the next day underconfident. Just things like this to optimize like your concentration and your like confidence in yourself when you're about to solve problems is very important to remember in the days leading up to an AMC.
yeah, I've been committing myself to getting going to sleep before 10, like these days, which is
That is very admirable. I have not started to do that yet. The 3 a.m. comment was in reference to me. I should start sleeping.
oh boy, high schooler moment, juniors moment. Yeah, it's kind of funny. I think because okay, here's a really actually kind of scary study that I read. So what they did, I know it's kind of overtime. What they did is they get college students because if you give them money, you can get them to do literally anything. College students, they split them into three groups, and they had everyone do like those sort of like mental ability like tests, like visual memory, reaction time, that sort of stuff. They had everyone do those tests. Okay, control group. Okay, we're gonna spend like a week like trying to find out how much sleep you need. Okay, like say 8 hours. Okay, we're gonna have control group go for 2 weeks, and I don't care what happens, you're getting 8 hours of sleep, however much you need, 8 hours of sleep. And we're just gonna test you regularly, and in 2 weeks, to no one's surprise, they did great, right? Group B, they had them stay up for what was it? I think it was two all nighters, which is 60 hours. Okay, I don't know if you guys have anyone pulled an all nighter before. Like one all nighter is already not fun to go about the next day. Um, and then that's two all nighters in a row without sleep, 60 hours without sleep. I don't remember if they had like coffee or anything like that. Probably didn't, right? They probably just slapped them when they were about to sleep or something. Then they did the test again. They did like every 12 hours. They could just see like there's to no one's surprise they did horribly, like really, really, really badly. Um, that was the second group. Again, they did not sleep for 2 nights straight. Group three, we're just gonna if take 2 hours off your sleep every night. So like if you need 8 hours, you're gonna get 6 hours, which is the situation for a lot of high school students. 6 hours. Okay, we're gonna have you do that for 2 weeks. These students, okay, who have like you're only taking off 2 hours in a day, right? After 2 weeks, they did worse than the group that stayed up for 60 hours straight,
That's
which
kind
is
of scary.
which is horrifying. Okay, because think about it. When you're after one all nighter, you know that you are just done. You can't do anything. Everything is going to be super unproductive. Like two all nighters, that's you're surviving, not living. But then if you keep like your 6 hours a night for 2 weeks, you don't notice. You can just say, I'm fine, like I'm tired, but I'm fine. But you're not fine. Like these results show that you're not fine. And so we are entering like an AMC test after like for me months, maybe for like high school months of not getting quite enough sleep. You accrue all this sleep debt, and then and you get back your test score. Like, well, I don't get it. Why didn't I do well? You know. So that's I just wanted to say that because it applies like not just to AMC but for everything as well. Like sleep.
Yeah, taking care of yourself is very, very important. It's like, it's kind of crazy how much of an impact that has on your ability to do things and your brain function. So like if you have not started sleeping well yet, um, me, then you should do that. AMC is coming up. Take care of yourself.
Yeah, sleep. I mean, it's kind of crazy how much shorter 6 hours feels compared to 8 hours. Like from the time you actually start to fall asleep to the time you wake up, it's actually kind of crazy um, sometimes. But like, yeah, I don't know what else to say because sleep debt has been like it's not just that study; they research it over and over and over again. But yeah, it's pretty conclusive that sleep debt is a thing. Um, anyway, that's. Do you have anything else to add?
Uh, no, I think we covered a lot of very good things. So I think we can wrap this up for today.
Yeah, and if you guys want more math, there's some math league live solve, not kangaroo, math league live solve tomorrow. I don't remember what time, but there's one, so hopefully we'll see you there. Um,
Yeah. And good luck to everyone taking the AMCs this week and next week.
yeah, good luck. Oh man, it's 4 days, four or
We'll
five
be
days.
fine. We'll do great. This will
We'll
be
be
wonderful.
fine. Yeah. There. Are you taking a paper or just online? Because they
I
have
am
like
taking a
this.
paper.
You're taking lucky. For those of you taking it online, I highly recommend like making a new burnout like throwaway email for it. Mostly because MA has some interesting security flaws regarding their website. Like you're like they make like hundreds of dollars from every school. That's like 300,000 students, right? They make a lot of money, but they can't
I think
afford
I
enough
think
to
this
get
might
like
be where a copyright strike might come from.
okay,
MA
I
is
won't say
great.
anything about MAA is great, but their website does have a minor issue that for a period of time, if you use someone's email without their password, you can just log in, which is like the worst cybersecurity flaw ever. Like it does not get much worse than that. So I'm just saying, like, make a new burn throwaway email that no one knows about, and then they can't log into your account. Just like just saying it out, putting it out there. That's what I did. So, yeah. I don't know bad their how good their website will be because they moved it, but there have been like issues with like rendering latex and stuff like that. Um, just good luck to everyone. Again, it's not the end of the world unless you're a junior and have no chance left, but even then, it's not the end of the world. Um, it's really just um, the way I look at it for like middle school, which hopefully most of you guys, I think most of you guys are middle school. Middle school math competitions are mostly just like the biggest, strongest impact for me is that like they gotten me used to taking high stakes tests for this sort of stuff. So when I go to take AP tests, taking finals, qualifying tests for that, that's really where it shines. Like it doesn't help for college applications. It's not the end of the world, parents. If you're watching this, it's not like the end of the world.
But
Um,
you do gain a lot of skills, and like you do gain some skills from like learning how to take tests, right? And like time management and resource management. But another really useful skill from doing math competitions is learning how to fail. Because at least in my personal experience, I have failed so often on tests. It is like if you compare my like stack of successes to my stack of failures, it's like the slope is very large, right? And like this is very valuable stuff to learn at a young age is like how to take all of these failures and rebound from them. And that's something that like will help you later on when you're tackling like big projects or things that have very large value is knowing how you've dealt with failures in the past and knowing applying that to how you will deal with failures in the future.
Yeah, yeah. So, like, there are some things that you should be thinking about before the test, and there should be things that you should not be thinking about before the tests. Um, so, yeah. I don't think it's worth saying much more on this. Just good luck to everyone taking the AMCs. Good luck to everyone. Good luck to MAA trying to grade everything and not face horrible scrutiny because that happens every year. We'll see y'all next time. Bye bye everyone.